So, good afternoon, everyone, and I'm pleased to introduce Professor Ravi S. Nanjundiah. We call him Professor Ravi, and just very brief. So, Professor Ravi, currently professor at Center for Atmospheric and Oceanic Science and Divecha Center for Climate Change. He was earlier my boss. He was, yeah, he's director at IITM, and but since 1990, he's doing actually global climate modeling. The seeds he has sown. We have developed a 6-kilometer global model now, but we've kind of followed his footsteps. He was not having any HPC that time. We have the privilege of having HPC now. Welcome, Professor Ravi, and very interesting talk. I heard it in Ashoka, I think. Heat stress, similar one. Heat stress forecast, we all will be interested. Floor is yours.
Good afternoon. Thank you, Dr. Partha, for the nice introduction. I should say that Dr. Partha himself is one of the major architects of a global forecast system, which is now running at 6 kilometers, what's called as the Bharat forecast system. And he's the major architect of it, and it's one of the highest resolution global forecast systems in the world. And I think its quality is comparable to the rest of the world. And to answer the question which I think somebody asked, I think the forecasts in India are much better, and why it is we think the Europeans are doing better, I think we can discuss it over lunch. Okay? Okay. So coming back to the work that we're talking here, it's about heat stress forecasts and its importance in presently changing climate. We know that climate is changing. So let's see how we can kind of use different techniques to improve the heat stress forecast. And this is basically a collaborative response that we are doing, where we are trying to bring in together climate scientists, health experts, doctors, disaster managers, policymakers, engineers, and frontline workers. And this is an initiative being led by IISc and the MS Swaminathan Foundation. And this is the whole set of people, which includes fairly well-known people like Dr. Soumya Swaminathan, former DG of WHO. And of course, yesterday, I think Professor Vijay Chandru had already given a blurb about my talk, and I hope I'll live up to the expectations of this one. So without further ado, I'll kind of go to what we are going to discuss here. I'll give a brief overview of changing climate, then how it will affect heat stress, and how we can leverage AI for heat stress forecasts. So climate change, the very basics. You can see how the temperature has changed over, let's say, I guess, 60 or 65 million years. And what I would like to say is that if we were, the climate change at the end of this century would be what would be about 50 million years back. So in the blink of an eye, we are turning the climatic clock by about 50 million years. That's the kind of change that we are likely to get. And if you're looking at an interim period, the temperatures are more or less constant. And if you look at the more recent period in the common era, it's quite constant. Only after about 1850 or 1900 did it start increasing. And today, if we were to look at, we have increased about 1.5 to 1.6 centigrade as compared to the 1850 values. So this is another picture, kind of a enlarged picture of the changes in temperature from different sources. So if you were to look at climate change, why is temperature important? It's not the only thing that we need to look at, but it kind of gives you a kind of a feel for how the climate is changing. It gives you a direct measure of the trapped heat, and it has a robust and long-term record, which you can easily look at. You can get it from various sources, how the temperatures are changing over the last million, or let's say the 65 million year is basically from a reconstruction. So you have a fairly robust and long-term record. And when we talk of policy, we can easily say that we are going to right now we are talking of a 1.5 degree containment. I don't think that's going to happen. We are already overshooting the 1.5. Last year, I think it was already at 1.6. I hope we'll be able to contain it to 2 degrees. Okay, and it's also a fundamental driver for other changes such as melting of ice, sea level rise, evaporation, atmospheric moisture, etc. I won't go into the details of that. So if we look at climate change, of course, there is natural variability. You have climate change which is human-induced, and also quite often we talk of local climate change and global climate change. So if you are looking at a feature which is worldwide, that's going to be the global climate change. If you're looking at a specific region or a city, that's going to be the local climate change, and the drivers for them are likely to be different. Global scale activities like changes in greenhouse gases, etc. And of course, land use, land cover, etc. That could be the local climate change effect. And quite often, when we talk of climate change, when we are looking at mega cities like Bangalore, I think the land use, land cover change which we are seeing could be kind of more than the global climate change which could be happening. But both of them are going, we cannot separate out. It's nature, so you cannot separate out the two. But quite often, when we look at regional cities, let's say in city and say that, okay, it's warming, it's partly the many factors that come into picture, which could be the urban heat island, etc. And I will not go into the details of it. But if you are looking at the impacts, global climate change is going to be widespread, and it has a long-term trends, while the local climate change is varied, location specifics, etc. And these are some examples. We talk of urban heat in Delhi or wildfires in California. And there are many other factors which are related to local. And without going into the details of it, we'll move on to what's of interest to us, which is the heat stress. These are some other basics. And quite a few people say that the climate change that we are seeing could be related to natural variability. This particular picture will tell you that if you just look at the natural drivers of climate variability, you will not get the kind of picture of increase in temperatures that we are seeing today. That kind of very categorically tells you that it's human-induced climate change, which is what the warming that we are seeing today. And this is details of radiative forcing. We think greenhouse gas effect, it's a word which is kind of a bad word in today's world, but it's also a good thing for us. If there was no greenhouse effect, we would be at a frigid minus 18 Celsius. Today we have at a more comfortable temperature of about 15 Celsius. And the kind of things that we are going to do is going to be over and above the 15 degrees that we get in the long-term equilibrium, and that's what we are calling as climate change. This is a brief overview of how we study climate and its variability. One of the major things that we use is the Earth system models, which combines ocean, atmosphere, sea, cryosphere, even land, various effects of land. They're all put together into a kind of a co-evolving set of models, which we call as the Earth system models. They are perhaps the most comprehensive and sophisticated models to study climate. And these are the major tools, or this is the only crystal ball that we can peer into and say that, okay, this is how the future climate is likely to be. And it's also one of the major tools that's been used by IPCC, the International Panel for Climate Change, Intergovernmental Panel for Climate Change, sorry. And its most significant statement, it is that it's unequivocal that human influence has warmed the atmosphere, ocean, and land, and widespread and rapid changes in the atmosphere, ocean, and cryosphere and biosphere have occurred. In simple words, it means that we are already experiencing climate change, and that's due to human activities. And these are the other details which, what I would like to mention is that we are close to breaching the 1.5 centigrade level. Last year, year-to-year basis, I think we were closer at about 1.65. But usually, when we talk of any particular level, it's a 5-year average. We have not reached the 1.5, the 5-year average, but I think we are more or less going to breach it by the time we reach 2030. And this is how the scenarios of global temperature into the future looks like. If you go with business as usual scenario, you will end up with a 5-degree warming. If we go with more conservative or let's say more sustainable ones, we may be able to limit it to about 2 to 3 degrees Celsius increase. So we have to be very, I think, aggressive, or let's say I guess now the COP30 is kind of convening, and I hope they come up with a consensus to kind of keep the global warming, the temperatures more into reasonable limits. And this is what and if you were to see whether the ESMs are giving you a realistic picture, this is the simulated warming at 2100 with 1 degree global warming, and sorry, for 2 conditions. This is what the observation shows, so it's largely in good agreement. And one of the things that you see that the warming is less kind of, you could say high, less you are seeing over in the Indian region, and that's because of the compensation of aerosols and GHGs, which might have reduced, which could have kind of reduced the heating. But in future, if we clean up our effects, and let's say if we want to say that, okay, breathe better, then we have to reduce the aerosols, and then we may see much more global warming also affecting India also. And this is how the pictures will look like when at 1.5 simulation, 2 degrees and 4 degrees. Basically, you see that the world will be going to be very inhospitable if we were to reach 4 degrees Celsius warming by the end of this century. Now I'll come to the major problem that which I'm going to discuss, and that's heat stress. And heat stress is a global problem. It's not just that it's unique to India, but since we have one of the highest population densities, it kind of stands out. India is one of the regions where heat stress is going to be having a maximum impact. And 2024 saw about 40,000 recorded heat strokes in India. And intensity and frequency and duration of heat waves is expected to increase worldwide. That's what the IPCC says. And of course, if you forecast, it helps the societies to be better equipped to understand, prepare, and respond to the evolving changes of heat stress on health. This is what WMO says. And if you were to look at the current forecasting in India, it kind of relies on fairly limited data, conventional models, and on meteorological variables. And hence, we believe there is an opportunity to leverage AI capabilities to improve forecasts, integrate additional weather data, and deepen insights for heat impact on health across communities. That's what we propose to do in this particular project. And if you were to look at how the climate impact on heat-related issues over India, it could face a dramatic increase in the frequency and intensity and duration of heat-related events, largely related by climate change, but also because of local land use and land cover changes, increased frequency and duration of heat-related events, and it's going to be widespread impact. Historically, regions which didn't have experienced heat waves or heat stress, such as southern and coastal states, example Kerala and other east coast, they are projected to experience heat waves more regularly. And warmer nights are likely to happen, and higher humidity, which is an even more concerning trend, because that would mean that the nights would be warmer, so you'll be more uncomfortable, and the heat that you kind of gain during the day, you will not be able to lose it very much at night. And there's going to be a major health crisis that could happen. The increased heat could lead to an increase in heat-related illnesses such as heat stroke, dehydration of chronic conditions, etc. Vulnerable populations could be outdoor laborers, the elderly, and those with pre-existing health conditions. And now that we know that climate change is already upon us, we need to take steps to kind of minimize its impact. We cannot undo it, but we need to kind of mitigate and kind of help out people. So that's what we would like to do, is to create accurate forecasts in short up to 5 days, and up to medium range, that is what we call as medium range in weather forecasting, that's up to 15 days. And it's very imperative that we do this. And this is one instance of heat wave which happened in 2015, and you could see large parts of India were affected, starting from Odisha right up to Rajasthan and up to the border of Pakistan. And temperatures were higher than about about 43 to 49 degrees Celsius. And so when we talk of heat waves, which were once rare, now they are now a defining feature of our warming world. So that's what we need to worry about. And if we can kind of improve the forecast that we can do for this, it would be a great thing. And if you were to look at the mortality from extreme weather events in India, what I would like to point out is the last column. And when we talk of forecasts, we've done a fantastic job about improving forecasts for tropical cyclones. There has been a 94% decrease in mortality rate. If you were to remember, those of you who have a long enough memory, or those who are kind of young enough, around 97, 98, we had a super cyclone in Odisha, which I think close to about 10,000 people died. And if we were to look at a cyclone in today's context, I think for the same intensity, I guess the deaths are about 4 or 5, or at best, let's say 10. That's the kind of change that has happened, and that's largely because of improvement in the forecasting that's happened in the last 20 odd years. But if you were to look at the mortality related to heat wave events, or the extreme heat stress events, there has been a 62% increase. That we have not been able to handle as yet. And if you were to look at the number of heat wave days annually at different states, and these are for various periods, and I would like you to see the last column, which is the latest one from 2010 to 2011. You could see that most of the states are experiencing more heat wave days annually. So that is a major problem that we are looking at. And these are some characteristics of heat waves in India. And if you were to look at when the heat waves occur, they usually occur between March to June, with high frequency over north and northwest India and central and eastern regions of India. And if you were to look at the reasons why heat waves occur, there are two types of them. The first one is where you have a heat wave over north central India, and it's related to the blocking over North Atlantic. It's a kind of a regional Terry correction that we are talking of, which causes, what happens over North Atlantic causes heat waves conditions over India. And the second type of heat wave is over the coastal region of India, that's more towards the eastern part, and what we call as a Matsuno-Gill response. In a sense, it's kind of a response to what's happening over Pacific, the central equatorial Pacific, which we call as the ENSO, or the El Nino Southern Oscillation. The causes could be remote. The impact is going to be local. Even if something happens in Atlantic or Pacific, heat stress is going to happen in India. And so we need to worry about how we can do a better forecast for heat stress. And if you were to kind of quantify what we mean by heat waves, the heat wave is simply a period of about unusually hot weather, typically of 2 or more days. Quantitatively, a heat wave can be defined as a prolonged period of excessive hot weather, which happens during the summer months. And the temperature increases suddenly as compared to the historical average. And as we discussed, there are many drivers of the heat waves, which could be related to land atmosphere exchanges, feedbacks on soil moisture energy, external forcings, and of course, in today's world, anthropogenic emission of aerosols. Aerosols can kind of cause localized hotter weather, because let's say if you're looking at emissions from transport, the carbonaceous aerosols that come out, they are likely to increase the warming locally. But of course, they have a short life period, and they can dissipate out within about 15 days, but they can also cause increase in temperatures. And if you were to look at heat stress and who is going to be affected, the link between death and heat wave is less apparent and more difficult to establish. Of course, the elderly, children, and people with problems, they are going to be particularly affected. And if you are looking at an Indian context, about 75% of the workers, which is about 380 million people, are going to experience heat-related stress. And extreme periods of high temperatures can lead to significant reduction in crop yields. Even agriculture is going to be affected, which could lead to a failure in many crops. And coastal regions of India, east and west coast, are found to be particularly vulnerable to heat stress impacts, which showing a perceptible increase in the number of impact days and a decrease of about 30 to 40% in the work performance, particularly over the eastern region. So it's not just a weather problem, and we have seen that it impacts certainly humans are going to be impacted, and there's going to be a cross-sector challenge which we need to worry about, which is like in the impacts on health systems, livelihoods, and vulnerable population. And there is a data gap. There's a lack of evidence to validate global heat stress metrics for India. This is something major problem. And again, I come back to what we are doing right now, which is a collaborative response, which it has many players in it, which includes government organizations like IMD, IITM, Government of Karnataka, and the State Disaster Management, and of course IISc and other agencies which are coming together to kind of trying to improve the heat stress forecast for Indian region, and initially we are trying to do it for Karnataka, and later on we would like to kind of extend it to the rest of the country. And this is the outcome we propose. So we have, right now we are just using only weather data, that's the status as of now. So, but of course some details of the person also comes into picture, which we can kind of use. And we use weather data which is from an AI-based forecast, like, so particularly of temperature, humidity, wind, and solar insolation, etc. And that, the user plus the human heat balance model, we can use that. And it kind of ingests the weather data and gives you risk scores, and then you have a advisory module, which gives you a personalized heat app, watch app, up to about 10 days forecast. The skill, of course, reduces dramatically after you go about 5 days, but it's reasonable in the first 5 days for the forecast. That's what we are seeing. And we are also kind of developing a public-facing dashboard, which gives you a 10-day forecast. Next, what we propose to do is kind of take field data, that is actually go to various sectors of the population, get household weather data and household demographic data, combine it with physiological data, which includes HR, sleep activity, core temperature, hydration, etc., and validate the heat risk score, which would be the first version of it, and then again have a human heat balance model with predicted HR and core temperatures, and then update the generic advisory module to give you a kind of a public-facing dashboard. And then you have a personalized heat watch app, which will take in your information also and give you a more kind of a selective information, which could be more kind of utilizable for the any particular person. So this is kind of a co-innovation and co-implementation that we are looking at. So we are looking at implementation, which is kind of going to be useful for various agencies. The data and engineering is going to come from various sectors, which includes IMD and some publicly available data sets. And the information for climate science is going to come from COS, IMD, and IITM Pune. And it combines data scientists, climate science researchers, and program teams. And the idea is to prioritize and define problems with insights to action, do a data exploration, and design and engineering, so that you finally get forecasts which could generate insights. So this is the approach that we are taking. Right now we are starting with the pre-trained AI model and do corrections for that, which includes bias and quantile corrections. I'll come to that in a moment. And then we could either use an individual model or an ensemble model and do a model evaluation, which kind of goes into the parameters for calculating heat risk, which could include temperature, humidity, wind, and radiation. That gives you a heat risk index. And also take data from, in the next step, we would like to take data from secondary sources and create a better targeted heat risk data. And also we'll also include information from heat vulnerability, heat action plan, and also mitigation strategies. All of them will come together. And what we want to leverage is going to be the AI revolution, which is a quite revolution, you could say that, and which has been trained on decades of reanalysis data. Reanalysis data is like you take all the observations together and put it through a data assimilation system, so that you have cleaned up kind of a set of data which is a proxy for observations, which is derived from the NWP systems. And right now what we are going to do, the data simulation, is again kind of linked to the NWP. It's not that we are replacing the NWP systems, but it's kind of using those NWP data which is coming out of the reanalysis and learn the statistical and dynamical relationships of the atmosphere so that we are emulating the physical processes to deliver forecasts. The idea is to kind of these forecast in a matter of a few minutes or seconds as compared to a longer period which happens with the numerical weather models. And this is the kind of prediction that you see from AI-based model, and its comparison with kind of what we call as reanalysis, which is kind of a pseudo data, or the closest you can get to observations. And we find that the 24-hour prediction of a quantity which we call as the integrated column water vapor, which Dr. Patra also mentioned, which is important, and it has a fairly realistic forecast. This is what the comparison shows. So it kind of gives us confidence that we can kind of leverage these AI-based models to improve the forecasts. And these are the set of forecast models that we are trying to look at. One of them is called the forecast net, which uses a Fourier neural operator, gives you an output for 10 days at 6 hourly intervals. And the output variables are temperature, humidity, horizontal wind. There's another one which has come out of China, which uses a vision transformer. It runs for 10 days again and gives you 3 hourly or 6 hourly outputs. And then these are the same variables that are being output. GraphCast is a model which is coming out of Google. And it again gives you a 10-day forecast. Another one is also from China, which is called the Fuxi, which uses a vision transformer, gives you a 15-day forecast, the same set of variables. And the last one with which we are comparing is the more like the gold standard for forecast, which comes out from the European Center. As far as global forecasts are concerned, the Europeans are the best in the business. And it's a gold standard. If you want to compare and see how well your model is going to do, the first question everybody asks you is how well it's doing as compared to the European Center or the ECMWF forecast. So that's what we are going to compare. And these are the results which it's showing. So this is the performance. We are kind of restricting over India. There are papers which talk about, for each of these models, they have given the global metrics. But what we are looking at is for the Indian region. And this is for the IFS high resolution forecast, which is coming at 10 kilometers. Most of the AI-based models are coming out at 25 kilometers. But their skill, even at a coarser resolution, is comparable or superior to that of the IFS HRES forecast. And this is the ensemble mean. Europeans do not do a single forecast. They do a set of 50 forecasts, and then they do an ensemble of that. And this is the one which shows the ensemble mean for weather. And so we can say that we can effectively utilize AI models. And the punchline I would like to say is that if I were to run this HRES model, or the kind of models which Dr. Partha has worked very hard to develop, I need a huge system. But if I take these trained models, I'm not talking of the training of the model, that needs a huge amount of effort. But if I take the trained models, I could just run it on a GPU-powered workstation or a laptop in a matter of minutes. What would take a huge resource to do a forecast, I could just do it on a GPU-powered workstation or a laptop. So that's the kind of a thing that we are talking of. And that's what I mean by the democratization of forecast. Just about everybody can do a forecast comparable to what's like the gold standard. And that you could leverage. And you could do 5 such models together while you are doing only one model when doing here for a numerical model. I'm not condemning numerical weather prediction models. I have worked all my life on NWP models. They have their own good things. But if you were to look at a particular forecast or something that you want to look at, then AI models could be a good alternative. That's what I'm trying to tell you. And if you were to look at which model does better, whenever I'm looking at a 15-day forecast, this is a comparison with what I called as the gold standard. This is the ensemble mean. And the color code shows that which is doing better and which is going to do worse as far as the RMSE is concerned. And on the first day, everybody is doing fine. When you come to the third day of the forecast, you can see that the AI-based models are certainly doing better as compared to the conventional models. And when you go to a longer period, let's say 10 days, Fuxi model, which is the AI-based model from China, seems to be doing much better than even the physically based models. So, and of course, I'm just talking about India and the things. I'm not, as I like to emphasize that I'm not condemning NWP models. They have their own advantages, and also, if you were to see, all of them are based on initial conditions which are coming out of an NWP model. So it's till we kind of reach a stage where we can kind of create the initial conditions based on an AI-based system, we are still going to be dependent on AI, NWP-based systems. Till then, I think NWP is going to be useful. And there are many other additional inputs that you get from an NWP model, both for research as well as for improving the forecast, which a conventional AI model may not be able to give you. Okay. So this is the correcting. All models have biases, and the bias is this is before just the raw forecast comes from various models. This is from Pango, this is from GraphCast, and we did what's called as a quantile correction, and the target was the European reanalysis data. And this is for entire India, that what we have looked at. And after bias correction, the biases are fairly small once we have done it. So which kind of gives us confidence that we can use these models even after doing bias correction, that it's a good alternative as a weather forecast system. And we propose to do this with the IMD data and on a more local scale for Karnataka, where we're using the graded data from the Karnataka State Disaster Management Center. And this is a typical, just a view of a particular forecast that we did some time back, and we are continuously doing it. And again, coming back, this is the overall picture. So what we have done right now is kind of gone into this particular level. And next, what is I'll talk about is the heat risk index. And the major problem that we have is that these heat risk metrics that we talk of, they are based on all data developed for, let's say, for European countries or America. Like one of the major metrics for heat stress, how a person feels heat stress, has been developed in the 70s for US Army troops. Obviously, we are not US Army troops running around with the same stamina, but those are the heat risk indices that we are using, and that's what is widely used all over the world, which is why we propose to kind of do this kind of a work where we look at various strata of the society and create heat risk index for various people. Let's say the heat risk index could be very different when you are looking at an outdoor laborer as compared to a person sitting in an AC room. So obviously, we need to have a proper heat risk index. That's what we need to look at. And that would also come to the mitigation strategies that we are talking about here. And one of the things that we are also doing is going to be a targeted heat risk dashboard, which I'll come to that in a moment. And the major problem that we are seeing is converting these forecasts into heat risk stress information. We can give you good forecasts of meteorological data, but converting it to heat stress, just as I said, is a thing that needs to be understood. And the conversion needs estimating heat stress, related discomfort, assume the physiology of a person, including their age, nature and of work and disabilities. As I just said, the indoor worker may tolerate heat stress much better than an outdoor worker. And also tolerance could be very different for people of different ages and coming from different parts. For example, if let's say European comes to India and he finds 35 degrees Celsius very uncomfortable, and it's going to be heat risk for him, but we can happily walk around and be very comfortable. So it again depends on where you are coming from and what is the what acclimatization that you have done. So these are various things that need to be taken into account when we talk of a personalized heat risk forecast or an assessment. And as I said, the current conversion formula are based on those conducted on US troops way back in the 60s. And so we need better estimators for Indian conditions that need to be developed, and we propose to develop this in information, we are trying to use a two-pronged strategy. One is to improve forecast of the meteorological parameters and also improve the conversion of these into heat stress parameters. And these are some of the heat stress indices which are commonly used. One is called the this is called the IMD's heat wave alerts, which just uses maximum temperature. And it's simple and useful for broad alerts, but it has limited use because it misses key drivers such as physiological stresses and even a major driver such as the humidity. For example, if you're in a coastal city, let's say like in Chennai, the temperature may not be very high, but the humidity is going to be very high, and hence you are going to experience higher heat stress as compared to a dry period with the same temperature. Let's say you're looking at Jaipur with 35 Celsius as compared to 35 Celsius in Chennai. You're going to be a lot more uncomfortable there at Chennai as compared to Jaipur. So that's where humidity starts playing a very major role, and that just a simple alert based on temperature is not good enough. Then there is an excess heat factor, whose major components are present and acclimatized temperature, and it identifies hot spells for early public health warning. It has its own uses. Then you have the heat index, which is an operational warning in USA, which includes both temperature and humidity, and measures perceived heat in shaded conditions and underestimates stresses in direct sun or wind. And there is one more which is very commonly used, which is called as the wet bulb globe temperature, WBGT. And it's an operational warning which is being used in Japan. It includes temperature, humidity, wind, and solar radiation, and is widely considered to be the gold standard for assessing physiological heat stress, which is widely used in occupational safety. And then you have the Universal Thermal Climate Index, UTCI, whose key component is a physiological model, best suited for evaluating outdoor thermal comfort and public health risk. And these are the formulae for the various metrics that just now I discussed. And as I just said, existing heat stress thresholds in India mainly come from studies in developed countries and may not reflect Indian conditions. So that's something we need to worry about. And that's what we are trying to develop with, in collaboration with the Swaminathan Foundation and other institutions to kind of do these field observations so that we get better India-specific estimates of which is relevant for our country. So now I'll come to the forecasting for heat stress in Karnataka, which we are using as a test case. And it's actually a very good test bed if you were to look at. Karnataka has a very heterogeneous region. It has coastal Karnataka, which is very humid, and southern Karnataka and northern Karnataka, parts of Bidar, etc., which is hot and dry, and of course southern Karnataka, which is very comfortable. So it kind of has various climatic zones which are kind of useful to kind of developing heat stress indices or do heat stress forecasts. And once we use it as a test bed, we can go to replicate it in other parts of the country. And these are the heat stress parameters which we just discussed. And this is over a dry interior region, and these are the various indices you would like. Since you are looking at a dry region, the WBGD is not very, these are for two different years that we have calculated it. And you can see that year to year there is a variation, but this is just an estimate that we are taking from observation. It's not just of a forecast. For a moist coastal region. And this is I would like to, can I click on it, please? I want to just show a quick what we are looking at as a heat health dashboard. Yeah. This is a real-time heat forecasting platform, and you can look at the current forecast. And you can choose any city if you like. Let's say you take, okay, I can't see, it should have Bangalore somewhere, but let's say we take a hot place like Bijapur, and it tells you where the heat stress is likely to be, forecast is likely to be more high. And let's say you look at a place like Bidar, where the temperatures are higher, and this is a 10-day forecast, which tells you the heat risk Of course, right now you are looking at a fairly comfortable season, so there's not much of a heat risk, but there's some kind of a heat risk over northern parts of Karnataka that you could see that. And the data from that, you could either generate a report and you could also download the data. And this data is kind of being kind of given real time to the Karnataka State Disaster Management, IMD, and various other organizations. For Karnataka, what we did is we took to do a hyperlocal forecast. We kind of combined data from the State Disaster Management Center, created a gridded forecast for that, and combined it, so the spatial, and also combined it with the AI-based forecast, kind of get a better hyperlocal forecast. The AI model gives you at 25 kilometers. Right now, we have kind of taken it to 10 kilometers. Later on, we would like to take it to a finer resolution, where we kind of merge it using a second level of AI. The first level of AI is already there in the AI-based model. Then we would do a second level of AI where you kind of do a hyperlocal forecast, merging the localized data, create another forecast, which gives you better skills. And this is the forecast that you are getting after downscaling of the data. And this is the 2-meter temperature that we are looking at. We have taken data from the Karnataka State Disaster Management Center, combined it with AI-based forecast, and to get a better forecast for the Indian region. And this is the kind of forecast that we are looking at in various metrics, which includes the scale Tmax, ground temperature, and Tmin. Those are the two major parameters that we look at. And these are some of the metrics for the forecast. This is the raw AI forecast. So this is the error. And after doing the downscaling, that is kind of including localized information and kind of doing a higher, finer resolution forecast, you can see that the errors are kind of reduced significantly from 3.68 RMSE to about 1.86 RMSE. And this is the kind of thing which Vijay also talked of. So basically, you can do a kind of a personalized heat app, which we can use it, and create your own files where you give your other details and also the health kind of parameters, and you can get a 7-day forecast based on this, which will personalize your forecast. Right now, we are just using the meteorological parameters. We are not doing it. Later on, when we actually kind of do the personalized, based on the kind of person work that you are doing, etc., that will be the second layer of heat stress forecast that we are planning to do in that. So this is the summary, and in effect, I would like to say that we can use AI, and anybody can do AI. It's like a democratization of the forecast that I'm talking about. We're also developing a dashboard, which I just talked about. And we propose, right now we've done it for Karnataka, we would like to do it for the rest of the country. And of course, we would like to increase the accuracy of the forecast. They are not perfect, but we hope to increase the accuracy of the forecast. And all the forecast outputs and data sets, the analyzed data sets, which we have built it ourselves, that's open to public. The actual, let's say, station data sets, because there are some constraints either from IMD or Karnataka State Disaster Management Committee, that we are not making it publicly available, but the rest of the data is going to be available publicly. And we are also improving the spatial and temporal resolution of the model, as I just said. So also having an interactive dashboard, example of which I showed, to disseminate forecast in a simple, actionable format for policymakers and communities. Thank you.
Thank you so much. I was just wondering, in terms of urban heat stress compared to rural heat stress, and urban heat islands, because even within urban areas you can have heat islands, and what your recommendations could be for architects and developers in terms of building design for different parts of the country. We all know that we are aping Scandinavian designs with glass windows everywhere because of so surely with the level of buy-in you have with the government, could you not take it to policy to inform, building codes, architectural designs, because you are already, at a higher level with maybe influencing these issues?
Well,
okay, I'll stop.
I mean, forecasting is an easier problem than the policy. For example, we know what causes problems in Delhi, the air quality, but there are no easy solutions. So, similarly for this, certainly we could talk to the relevant policy authorities, but whether they implement it or not is a question which I don't know, I cannot answer. But certainly we can improve the forecast and kind of create better assessments for personalized heat health. But when it comes to buildings or urban heat islands, of course we could kind of do hyperlocal forecasts. We could do that kind of a work, but giving recommendations and them being followed, you know what's happening in Bangalore. So, I mean, there's violation of laws everywhere, but I don't want to get into it. Okay, yeah.
So I have a question. You may have said this and I may have missed this. What is your definition of heat risk? How do we define risk?
Okay, there are various metrics that I just now pointed out.
So what goes into the definition of risk?
Okay, let's say if I were to look at it from a meteorological point of view, essentially it's going to be winds, temperature, humidity, and combination of these. And supposing you want to personalize it, you bring in the person's age, his pre-existing disabilities, etc., and you combine it with some, let's say, some already existing, let's say, the formulae or whatever the research has already been done. You combine that to give you a kind of a heat stress, and based on the temperature and others, you can kind of tell them what is the heat risk they might be feeling. Let's say if you're at 35 degrees or 25 degrees, heat risk might be very low. But if you're going at 35 or 40 degrees Celsius, the heat risk is likely to be higher. But if you are, let's say, young and energetic or athletic, the heat risk could be still low. But let's say somebody like me who's much more aged, the heat risk could be very high.
No, is that all? Obviously, you're talking about a regression equation. Is all of that taken into account?
Okay, I could. Those were the ones which I mentioned, but I kind of rushed through it.
Okay, maybe we can talk. It's getting technical, so maybe we can talk about it after or during lunch break. Thank you.
Yeah, these are some of the equations that we are using for heat stress indices. Yeah.
From your diagram, I think one of the figures was the effect of this one, temperature rise is going to be felt more in the northern hemisphere because that is what was.
Okay. Northern hemisphere is more continental. The southern hemisphere is oceanic. So the effect is certainly going to be held more in the northern hemisphere. And of course, if you're looking at the population, most of the population is in the northern hemisphere. So it's going to be having a bigger effect there. And and I guess land temperatures would rise faster than the ocean temperatures. So you may, if you're looking at global the variation of temperatures, it could be higher over the northern region as compared to the southern region.
So we are safe. I mean,
we are actually not safe.
No one is safe.
We are in more trouble. Yeah.
Just wanted to make a quick comment, and Rennie, this is related to what you had raised. As part of the team, we also have the Center for Sustainable Technologies, Monto and others from IISc, who are advising on vernacular architectures and ventilation and so forth. And we were also working with CSE and IUDI on actually advising architects on some of these issues. So it's being done as a wholesome project, but yeah.
Sorry, I forgot to mention. Yeah, we are also working with CSE.
So, like cyclones are relatively short duration events, right?
Yeah.
So the government can move people out and over the area, but what for heat stress? It happens over probably extended period, and people cannot be really moved out, presumably, in the same way. So what? How?
That's where I think the advisories come into picture. If you can give them better assessments and give better advisories, maybe they can take appropriate action to kind of make themselves safer. I
But
think that's
people who
what,
are at work, I mean, they probably don't have too much
that's
option.
a major problem. Like an outdoor worker, temperatures are going to increase. It's a major problem for them, but we can only, at this stage, we can only advise, but we can tell them what they can take, maybe drink more water, go into shade more often. Those kind of advisories we could tell them about that.
Two short questions. Here.
Sure.
Is the air pollution included in your modeling? I mean, the AQI and so on. And number two is why the mortality rate due to lightning went up, 52%.
Well, I mean, okay. First question I can, right now we are not taking AQI into consideration. It's a tougher problem to handle. I mean, many people have asked us about including AQI for heat stress. The two are related. But, just doing plain heat stress has been a problem. So including AQI, which has even more uncertainty when you are going to do a forecast, we have not yet done. At a future stage, we certainly would like to do AQI also. And as far as the lightning is concerned, it could be related to more number of thunderstorms which are happening. And also maybe people are out more into the open and doing farming operations. And in general, the population has increased over a period of time, so the likelihood of getting being struck by lightning could be higher. But I think here is an expert on thunderstorms. You can discuss with him and he can answer it more.
Lightning issue is we are not able to reach the last mile.
I know. It's also a problem of...
A farmer on the field doesn't carry any mobile. Okay? So, whatever way you give the message, it doesn't reach him. And he is the most vulnerable on the field. So that's why you could see 52% rise. That is one of the major bottleneck. We are not, I mean, it's from ministry, from government, how to reach the last mile when a person is on the field. Still it is open question. We could not close.
We are actually, I think IITM is doing a lightning forecast.
Things are,
and they are also kind of putting out on mobile, but I mean, it may not be reaching them.
If you see the slide, you will see the skill has improved, but the death also has improved. These two doesn't go hand in hand because so the skill is not getting translated into the end user.
Same thing is for the people in the sea when they go in the port.
True. So last question from a comment from Professor Gould.
No, I was just wondering that three effects that, considering that risk essentially means, all potential losses that could take place. And I was thinking that three items, and none of these are so easy to quantify. One is the loss of productivity, industrial productivity or whatever. The other is the debility, general debility amongst people. And the third, I was wondering, since respiration increases faster than what photosynthesis could do, what would be the loss in the productivity of the, general? I mean, these will be, I'm sure they need researchers. There are no easy answers to this.
Yes. Much research needs to be done. We can only, existing whatever literature we have, we can use it. But as I said, we want to do that kind of a thing where we look at the last mile, look at the actual people for different strata of society and try to get better heat risk, health heat risk indices kind of tailored for them, let's say for an outdoor worker as compared to people inside, for various, let's say old people, children, etc. We would like to do that. We are going to do a kind of a sample survey in Tamil Nadu and Karnataka, but that is yet to be done. We have not yet started it. So that's the proposed work that we are planning to do.
So thank you, Professor Ravi. Let us give a big hand to Professor Ravi. Somebody.